Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll. Today's big idea, quantum mechanics. You knew this was going to happen. This is one of the biggest ideas we have. Like a previous idea, time, quantum mechanics is something about which I have written a book. So you can buy the book, Something Deeply Hidden, Quantum Worlds and the Emergence of Space-Time, wherever you can buy books. And to be honest, quantum mechanics is such a big topic that it's going to be more than one idea. But in this particular video, what we'll be talking about is sort of the black box, the recipe, what we teach our undergraduate students in physics classes about how to use quantum mechanics, okay? Then there's deeper mysteries about how quantum mechanics really is, what the ultimate description of reality, according to the quantum viewpoint, should be thought of as, and that will come in a subsequent video. But right now, how to use quantum mechanics. So by the time this hour is over, you'll be at the level of a sophomore at Caltech or something like that, minus some mathematical details. And I don't want to be too historical about it. We've never been very historical in these lectures, but we can be inspired by history. So I'm going to move into quantum mechanics in a sort of pseudo-historical way. And the reason for doing this is because quantum mechanics is so radical, is so different. It's such a big break from the previous way of doing physics that it really is important to motivate it, not just to state what is going on. Unlike special relativity, where I just sort of told you the answer, in quantum mechanics, I would really like to see why that is what the answer apparently is. And then, maybe you'll be empowered to think about other ways that it could be. However, I'm not going to stick to the actual history of quantum mechanics too much. It's too rich, too interesting, too complicated. There were all these brilliant minds arguing with each other. We're going to do a simplified version of quantum mechanics. And, the reason for all of this throat clearing is quantum mechanics is special in the whole world of physics, in the whole set of physical theories ever invented. Everything we've been talking about up till now has been in the context of this classical paradigm for doing physics, handed down to us by Isaac Newton and others. Quantum mechanics is a replacement for classical mechanics. No one before the 20th century thought that classical mechanics would need to be replaced. It was just working so well. Everyone thought it was just going to be a matter of figuring out what is the specific version of classical mechanics that we would need. So quantum mechanics comes along. It tells us something completely different about the world, and that thing is so completely different, so alien to the ways that we think, that even today, we don't claim to really know the final answer for what quantum mechanics is all about. So that's why we need to break up the discussion into sort of the accepted parts, the used way that we approach quantum mechanics, and then the deeper parts that are still controversial. We don't actually know many answers to questions that are very easy to ask about quantum mechanics. So that's why it's so important. Quantum mechanics is simultaneously absolutely central to all of modern physics, and yet something that we don't claim to understand. So to get there, the way I like to do it is to actually imagine a fake history, physics that didn't actually happen. So this would be if quantum mechanics hadn't come along, where were we going? What is the sort of idea of what physics is that people might very reasonably have had near the end of the 19th century, beginning of the 20th century, but things didn't work out that way because quantum mechanics got in the way. So the thing that we would have thought, classical physics, right? And again, as I've said before, we usually illustrate classical physics with particles, doing things with positions and velocities, but it works equally well for things like the electromagnetic field. In the middle of the 1800s, Maxwell and Faraday and others worked out the theory of electromagnetism, which is a field theory. It doesn't fit into Newton's idea of absolute space and time. Electromagnetism was the inspiration for Einstein and others to invent special relativity. But the basic paradigm of things with positions or configurations and also with momenta that you could solve equations for and predict the future deterministically, the clockwork universe, all of that was perfectly compatible with everything that electromagnetism said. Even statistical mechanics, which came along at the same time in the 1870s, again, Maxwell, but also people like Boltzmann and Thomson and Gibbs and so forth, it was a slightly different paradigm because in statistical mechanics, you imagine you don't know for sure what the positions and velocities of everything are, but you still think that there are such things as positions and velocities. So it was still basically the classical paradigm. So that's the direction in which people were going. And they thought that you could say that matter in the universe, the stuff of which we're made, was made of particles. So we had, by the end of the 1800s, we already knew about the electron. We were soon going to figure out something called the Rutherford atom, which we'll get to in a second. But we didn't know about protons and neutrons yet, but those were coming very soon. But we knew about atoms, and atoms had been thought of as particles in some way. So the point of a particle is, this is going to seem like a little bit too much detail, but it'll be useful later. If this is space, a particle is something that has a location. There it is, x, and I'm going to put a little vector sign because it's in three-dimensional space. At any one moment in time, a particle is here, it is not anywhere else. And along with the matter equaling particles, again, physics that didn't happen, you had the idea that forces were given by fields. We already, of course, had seen the gravitational field. Laplace had figured out that you could do Newtonian gravity in terms of a gravitational potential field. Faraday and Maxwell and so forth showed that electromagnetism fit into the same paradigm. And unlike a particle, a field is sort of the converse of that. Fields are everywhere. So sort of, if this is space, the field exists at every point in space, okay? In particular, at every point in space, the field has a certain value. And what matters for the field is not where it is, because it's everywhere. What matters is what the value is and how the value changes from place to place. So at each point in space, like that point right there, you might have, for example, an electric field, which is itself a vector, and it's located at that point in space at that moment in time. So you have particles with locations, you have fields that are spread all over, and roughly the picture that was arising was particles move around being pushed by the forces generated by the fields. So for example, if you have a proton, which is a positively charged particle, you have an electron, which is a negatively charged particle, there's some pull between them, which is a force due to electromagnetism. They pull together. They also pull together due to gravity, whereas if you have an electron and another electron, electromagnetism pushes them apart, gravity pulls them together. And so you had this complicated but really very rich picture where particles interacted through different forces, which could compete in different ways, and therefore give rise to all the complexity of life around us. It was a pretty darn good picture. And furthermore, there was some unification of known ideas within this picture. So let's say you have an electron, and an electron has an electric field. The electric field goes around and actually points toward the electron because it's negatively charged. If it were a proton, a positively charged proton, the electric field would go out, electron it goes in. And you can take that electron and you can move it, right? Well, imagine that you do move it. Imagine you shake the electron up and down. So the electric field here, this is the electric field surrounding the electron. If you shake the electric field wants to be pointing toward it, but if you move it, it takes time for the electric field to realize, oh, the electron has moved, I should shift where I'm pointing toward, okay? In Newtonian gravity, if you move a planet, the gravitational field changes instantaneously all throughout the universe. But Maxwell and others showed that this change in the electric field, and likewise a change in the magnetic field, does not happen instantaneously throughout the universe. It propagates outward at the speed of light. And that's because if you take this electron and shake it up and down multiple times, the electromagnetic field vibrates, it pulsates, and the disturbance that you have created in that field propagates outward in the form of a wave, and it moves at the speed of light because that's what light is. Light, as Maxwell showed, is a wave of electromagnetism. So the electric and the magnetic fields vibrate, and we see that as light of different wavelengths, of different colors, for example. So that's nice. You can see how, something that you didn't know whether it was a particle or a wave, namely light, you say, now we know what it is. It's a wave. Newton thought that light were particles. Light were what he called corpuscles. He had evidence for it. He said when you have your hand near the ground, it casts a shadow with sharp edges. The light doesn't go around like waves do. But it turns out that's just because the wavelength of light is very, very short. So light is a wave in this field. Electrons, which are particles, created. It's a very nice picture that is coming together. Sadly, around the year 1900, not so sadly, but remarkably, around the year 1900, this picture begins to fall apart. And it falls apart in two different ways. Falling apart, this picture. And how can it possibly fall apart? Well, we could question classical physics, but we're not going to do that yet. We could question the particle nature of matter or the field-like nature of forces and light. So it turns out we did both. We showed that light has particle-like properties. This is very vague sounding, but that's important that it's vague sounding because when we came up with the idea, we didn't have the full theory. It wasn't like you went from classical physics, boom, to quantum mechanics. We sort of clawed our way up very gradually, and so we made all these vague sounding statements before the whole thing finally clicks together. So what does this mean? This is the phenomenon of blackbody radiation. And the people who figured it out were Max Planck. I'm very inconsistent about whether I pronounce German and generally foreign names correctly or not, but it's Planck. If you were Mr. Planck, Professor Planck, that's how he would pronounce it. And of course, Einstein also came along to clean things up, as he so often did. So the point is that a black body is just something with a temperature, okay? You know, when you look at things in the world, you see they have colors and textures and all that stuff, but you're seeing light reflecting off of it. There's also the glow that the objects give off intrinsically. Usually you don't see that because room temperature objects glow in the infrared and your eyes are not attuned to the infrared. But if you heat something up so that it glows in the visible light, then you can see it glowing, and that's black body radiation. And the nice thing is, it doesn't matter what the thing is made of. Black body radiation is exactly the same for everything. The problem was, if you took this paradigm, matter is particles, so there's all these vibrating atoms in the object you're heating up. Forces are fields, so light is a wave of electromagnetism. You could calculate how much energy should come out in the form of black body radiation. And furthermore, you could calculate at what colors it comes out, right? We know that long wavelength light is toward the red end of the spectrum, short wavelength light is toward the blue end of the spectrum, and we have ultraviolet, which is even bluer than blue, very short wavelengths, invisible, and we have infrared, longer than red, even lower wavelengths, longer wavelengths, lower frequencies. So it turns out that there was what is called an ultraviolet catastrophe. It was only called that later, but that's okay. By, I think Paul Ehrenfest called it that. The classical theory of blackbody radiation predicts that there should be an infinite amount of energy being given off at very, very short wavelengths from a black body. That is clearly false. It is clearly not what actually happens. And so it was Planck who came along and said, you know what, I'm just going to guess. I'm not exactly sure what his thought process was, but his guess was, rather than being emitted in smooth, continuous waves, the kinds of light that was given off by a black body came in discrete chunks. There was a certain amount of energy given off one at a time. It was not smooth and continuous. It was quantized in some sense, okay? This is the beginning of quantum mechanics circa 1900, when Planck first made his suggestion. And his suggestion was that light comes in chunks of energy, and the energy depended on the frequency of the light. E, the energy of each little chunk of light, was a new constant of nature called h times the frequency. H is cleverly now called Planck's constant. And it joins things like the speed of light and Newton's constant of gravity as a fundamental feature of the natural world, a fundamental parameter of physics. I will tell you a little secret, not much of a secret, but a little trick. Usually in physics, we define the angular frequency omega. So f, the frequency, is literally how often things go up and down. You multiply by 2 pi to turn that into an angular frequency. So omega is 2 pi times f. That's the angular frequency. And then we define h bar to be h, Planck's constant that he invented, divided by 2 pi. So E is h bar omega. And this is a very famous formula, Planck's little formula. And what Planck is saying, remember, is that black bodies are giving off light, giving off radiation, not as a smooth wave, but in chunks. He didn't quite go so far as to say that that's because light is individual particles. That was Einstein. Einstein came along and said, forget it, not just black body radiation, but in other contexts, in the photoelectric effect, for example, light comes out in these quanta because light really is particles. And so we now call these particles of light, we call them photons. Another thing that the name nomenclature came along later. Okay, so that's interesting, but it was also disturbing because, you know, literally one of the greatest triumphs of 19th century physics had been understanding that light was a wave in the electromagnetic field. Here's Einstein and Planck saying, well, light also has a certain particle-like kind of behavior under certain circumstances, and it involves this new constant of nature, Planck's constant, and it has sort of a quantum feeling. Quantum just meaning a discrete unit of something, okay? So that was in the back of everyone's mind. That is something that is going on. That was fact number one. Light has particle-like properties. Fact number two that people began to discover, matter, like electrons and atoms, has wave-like properties, or field-like properties if you want. Where did that come from? Well, remember this picture that we had, that we were putting together of classical physics, the world that could have been, but that didn't actually happen, featured a bunch of particles interacting with forces, and they came together to make atoms. So it was the Rutherford atom, named after Ernst Rutherford. That is the famous picture you always see. So the Rutherford atom has, you know, protons and neutrons in it. There's a proton, 2 neutrons, and then there are electrons circling around in orbits, circles or ellipses or whatever. It's kind of like a little solar system, okay? That's the Rutherford atom. And he got this experimentally by shooting little helium nuclei at gold foil and seeing that sometimes they recoil by a huge amount, as if the helium nuclei had hit something small and dense and hard to move, namely what we now know of as the nucleus of the atom. And this is a very successful picture. This is so successful, it's used basically as the symbol for physics even today, right? The Rutherford atom, this famous picture. The problem is it can't be right. We knew instantly that this picture couldn't possibly be the right answer. Why? Because we knew that if you take an electron and move it, it gives off electromagnetic radiation. That's where light comes from. Literally all the light around you right now is coming from vibrating electrons. And in this Rutherford atom, you have electrons moving in circles to beat the band. That counts as moving, okay? That counts as vibrating. These electrons should be giving off light. So if I move this over here, this is the picture that Rutherford thought was the case. But what actually should be the case is something more like nucleus at the center, protons and neutrons. And what the electron should be doing is spiraling into the center very, very quickly. Why? Because as the electron is moving, it should be giving off light. It should be radiating. That's a terrible looking photon I just drew there. Can't really draw it from right to left very well, so I'm going to draw it this way. It's giving off photons. It's giving off light at all times. It's losing energy. It's spiraling into the middle. So every atom in the universe, if Rutherford's model had been correct, should be wildly unstable. How long does it take for all the electrons to fall into the center of the nucleus? About 10 to the minus 11 seconds. So 1/100th of a billionth of a second. So all the matter in the universe, including you and the tables and Ernst Rutherford, etc., should be dramatically unstable. That seems to not be how things actually are. So this was a challenge. This was a challenge to this otherwise super duper successful way of thinking about particles and forces and so forth. What to do about it? Well, there were other clues. There were clues from how light is given off by gases, spectral lines, and so forth, that led Niels Bohr to suggest a modification of the Rutherford atom. Niels Bohr actually served as basically a postdoctoral researcher in Rutherford's lab for a little while. And Bohr said that you have the nucleus, just like Rutherford thought, okay? But rather than the electron being just a particle that can be anywhere, there are certain allowed orbits that the electron can be in. And other orbits are just places where the electrons are not allowed, okay? So the electron can be there, or it can be there, but it can't be in between. That's just the rules. Why? Because Niels Bohr said so. This is circa 1913, approximately. And, well, you might want to ask, why is that true? And Bohr's answer was he didn't know yet. He was just making a guess, like Planck made for blackbody radiation. You might also say, well, what orbits are allowed? Okay. The answer is if this distance is r, the distance from the nucleus to the electron, then the angular momentum of the electrons turns out, if you want to fit the data, if you want to understand the light that is given off by these gases, the angular momentum, which is given by just the ordinary momentum p, so you have some electron moving here with a velocity, and so it has p equals mv. Momentum is mass times velocity. You can special relativityize all this stuff if you want. That's the Newtonian version. P times r is the angular momentum. And Bohr just says, you know what? This quantity, the angular momentum of the electrons going in its orbit, is quantized because I said so. And what units is it quantized in? It is n, so that's just some integer, some number, 1, 2, 3, 4, etc., times h, times Planck's constant. So that's where you begin to think that something miraculous is happening, right? Planck came up with his constant by saying that light, which is supposed to be a wave, has particle-like properties, and you need to introduce a new constant of nature to fit the data. Here, Bohr is saying that electrons, completely different phenomenon, have to be quantized in a different way. Only certain orbits are allowed, but to fit his data, to fit the data that he cared about, not the data he collected, he was a theorist, but to fit the data that he knew about, the quantization condition, the chunkiness of which these electrons had to participate, was also characterized by the same number as what Planck came up with, the same constant of nature, Planck's constant. By the way, you might want to know, what is the number, Planck's constant? It's some number of joules, seconds, whatever it is. I have no idea what it is because every good physicist sets h bar equal to 1. Just like we set the speed of light equal to 1, and then we get on with our lives because no one remembers how many joules or whatever per second h bar is. So we use much more sensible notation than that, and therefore, in fact, it's almost impossible for me to remember where the h bars go in almost any equation. So if I write down equations and I forget the h bars, that's because in my brain they're set equal to 1. Okay, so that's evidence that something is going on. I mean, it seems like a little kludgy, right? A little ad hoc, and it seems like you're doing violence to the fundamental principles of classical physics, and that sounds bad. But it also seems to fit the data, and it was sort of nicely consonant with what Planck and Einstein had said, so that sounds good. But you still want to know why something like this is true. And the answer came along from a couple people. The answer is basically that, like we said up here, matter has wave-like properties. So the answer is that rather than just thinking of the electron as a little particle moving in a circular orbit, think of matter waves. And the first person to say this out loud was Louis de Broglie in his PhD thesis. So, those are the standards for the PhD thesis. If you're Louis de Broglie, you say electrons are waves, not particles, okay? And what he says is, very much like what Planck said and Einstein for photons, for particles of light, he said that you can associate a wavelength with an electron. The wavelength, lambda, is the de Broglie wavelength, and guess what? It is h, the Planck's constant, divided by p, the momentum. So a fast-moving particle has a short de Broglie wavelength. A slow-moving particle has a very long wavelength. Why? Why is this an interesting thing to say? Well, if you go back up to Bohr's atom, to Bohr's condition, the angular momentum has to be a certain amount, and you say, well, I'm going to interpret that as saying that when the electron does an orbit, there needs to be an integer number of de Broglie wavelengths around the orbit. okay? Then you get Bohr's quantization condition. You get it. I'm not exactly sure. I'm looking at my notes here. I didn't actually write down these equations, so I might get 2 pi's in the wrong place. Sorry about that. But the point is that if you just take the idea that an electron has a wavelength, and then you say the only orbits for the electron that are allowed are those that have an integer number of wavelengths, then you naturally get that only certain orbits are allowed, others are not. That fits the data in exactly the way that Bohr had wanted to. So Bohr had this phenomenological relationship, right? Certain electron energies and orbits are allowed, certain ones are not. De Broglie is trying to explain it by saying the reason why you get these energies is because electrons are waves. So from both sides, our classical intuition is being attacked. We thought that matter was particles, and we thought that forces were fields, and we're realizing that matter has wave or field-like properties, and waves have particle-like properties. Okay. So it was all put together. I'm going to, again, since we're not being historical, the first really full-blown quantum mechanical theory was called matrix mechanics. It came from Heisenberg, Born, and Jordan. And physicists didn't like it. Like Einstein said, this is just mathematical jiggery-pokery. Like, I don't understand what they're saying. This is Einstein saying, this is too mathematically complicated for me. But very soon after that picture came along, Schrödinger comes along with his picture of quantum mechanics. And it turns out to be equivalent. Schrödinger and Dirac and others show that these two ways of doing quantum mechanics are equivalent, but Schrödinger's way is just much more comfortable to physicists because it's a story of waves, not of matrices. Matrices are mathematical objects. Their physical meaning was not very clear. Schrödinger comes along with waves, and physicists knew what to do with that. They were very happy with the idea of waves. So Schrödinger says that we should have these things called wave functions. And he didn't even, as it turns out, the way that he thought about it wasn't exactly the right way early on, but still we keep the idea. And he had an equation, the Schrödinger equation, which tells us how the wave functions evolve. So what is going on? What's the difference here? I mean, de Broglie says electrons are waves, but he didn't give a dynamical equation for how those waves evolve. If you had asked, how do 2 electrons bump into each other and scatter off, he wouldn't have been able to tell you that, okay? The classical paradigm that we've been working with before is given juice by this idea that if you tell me the positions and velocities of everything in the world, then Newton's laws or Hamilton's equations or the principle of least action or whatever will tell you how to move them forward in time, how to evolve them in time. That's the kind of equation you want to turn these ideas into a full-blown physical theory. So that's what Schrödinger gave us, and also what Heisenberg and Born and Jordan gave us. They gave us a way of taking initial conditions and being a quantum version of Laplace's demon, of saying from those initial conditions what happens next. So Schrödinger's wave function, capital psi, the Greek letter psi, is a typical way of writing it. So for just one particle, let's just take one electron. We'll make the world more complicated later on. So it's a function of where the electron could be and when. So it looks very much like a field on space-time, but there's subtleties that we'll get to, which is why we don't call it a field. We call it a wave function. That's what it is, or the quantum state. So AKA, also known as the quantum state. And just as a mathematical fact, at any one point, the wave function is a complex number. So this is a real number plus an imaginary number. Imaginary numbers are proportional to I, which equals the square root of minus 1. So you're going to see i's, square root of minus 1, all over the place in quantum mechanics because the Schrödinger's wave function is a complex valued thing. I'm not going to get into any of those mathematical details, but you should know that that's how it works. Okay. And what Schrödinger says is, I'm going to describe the electron as a wave, this complex valued wave function. I will tell you what equation it obeys. And to tell you that equation, I need to remind you of the Hamiltonian. Remember the Hamiltonian? The Hamiltonian, in classical mechanics, h is a function of x and p. So you give me the position and the velocity, and for some physical system, the Hamiltonian tells you how much energy it has, right? So in quantum mechanics, you don't have x and p. You have the wave function. So remember, x in this, when I say here x, that is any location in space that the particle could be subjunctively, right? And p is any momentum that it could have. I can assign, via the Hamiltonian, an energy to that particular state. In quantum mechanics, the state is not a particle with a position and a velocity, it's a wave function, okay? That is the state. So this psi of x and t replaces x and p here, okay? So we want to know what the Hamiltonian is of the wave function, okay? Not of a position and a momentum. So what Schrödinger figured out how to do that, okay, basically, and we don't need to go into the details. There's some math involved, some derivatives, some calculus, as you might guess. And Schrödinger said in quantum mechanics, you should treat the Hamiltonian as an operator. So we put the little hat on it to indicate that it's an operator. What that means is, rather than just evaluating it and getting a number, you act it on the wave function to get a different function. So you give the wave function, psi of x all over space, evolving through time, but you just give it to me at one moment of time, okay, so psi of x. The Hamiltonian says, I'm going to act on it, I'm going to operate on it and give you a new function, okay? And then Schrödinger gives you some mathy facts about how that happens. And then he sets that equal to I, square root of minus 1, h bar, Planck's constant, the reduced Planck's constant, h over 2 pi, times the derivative of psi with respect to time, d psi dt. And this is the funny d's of partial differentiation that we talked about before. So this is Schrödinger's equation in its most general form. I'm hiding a bunch of details in the letter capital H here in what the Hamiltonian is. Every physical system will have a different Hamiltonian, just like in classical mechanics, okay? But the point is, this is an equation that answers the question, you give me the state, namely psi, the wave function. This equation tells me how it evolves in time. So this is the equation that is being solved by a quantum version of Laplace's demon. This is the equation that tells you how the trajectory of the wave function travels through the universe, through time. Cool, that sounds good. Now, once you have an equation, it's full employment for physicists, right? You can just solve that equation, you can give it as homework to your students. Boy, does that happen a lot, because there's a lot of very interesting situations. You might want to say, okay, solve this equation for an electron in a hydrogen atom. That's actually pretty easy to do. Solve it for 2 electrons in a helium atom. Turns out to be really hard because the 2 electrons are bumping into each other in some way, but you can do it, okay? Again, full employment. You can, in principle, answer whatever question you have. That's the usefulness of this equation. What it doesn't tell us is what is psi. You know, how should we interpret it? How should we think of this wave traveling through space? After all, didn't we have good reasons to think of electrons as particles in the first place? And now you can't just say, well, no, they're not particles, they're waves. You have to explain to me why I should believe that and why they ever looked like particles in the first place. So the first step is, after all, let me also mention one interesting thing. The whole business about the Bohr atom and the blackbody radiation and all that stuff seemed to be a story of taking smooth, continuous things and making them discrete, right? Chunking them up. That's where the word quantum comes from in quantum mechanics. And here in the Schrödinger equation, you have a wave function that is smooth and continuous, and you have an equation that says how it smoothly evolves through time. There's nothing chunky or pixelated or discrete about this at all. Where does that come from? The answer is, I'm not sure how good a job I'm going to do with this, but I'll try to explain what the answer is. The answer is you solve this equation for what the wave function of an electron is doing when the electron is sitting close to the nucleus of an atom, okay? If the electron is just out there in the middle of space, then there's nothing quantum about it. There's nothing quantized, discrete, pixelated. It can have any energy, it can move in any direction, the wave function can be spread out all over. But basically, when you put it in a box, which you can think of the nucleus as doing, then the discreteness shows up. Imagine you literally have a box. So this is just an analogy, okay? Box analogy. And you have some, and you have, I don't know what to say in here. Let's say you have a string, attached to two different sides of the box. So the box isn't doing much except holding together the two ends of the string. Now you can vibrate the string. The string is analogous to the wave function, okay? The height of the string is psi of x. And you can pluck it like a violin string or a guitar string, and it will vibrate. But you know that there are sort of different vibrational modes allowed. So there's one mode where it just goes up and down in a simple way like that, okay? But there's another mode where it sort of has twice the frequency and half the wavelength. And there's another mode where it has 3 times the frequency and so forth, okay? So the point of these little pictures are that the solutions to the vibrational states of the string, given that we have tied it down on both ends, come in a discrete set. There's the lowest wavelength, the longest wavelength, half that, a third of that, etc. The electron near the nucleus of the atom is like that. It's not quite in a box, but it's snuggled down there near the nucleus. It's being held in there by the electromagnetic force. Its wave function tapers to 0 very, very far away. And so the allowed wave functions that solve Schrödinger's equation for an electron near the nucleus of an atom are discrete. There's a lowest energy one of one higher energy than that, etc. And you can go through and you can derive the Bohr atom. You can derive these conditions that the angular momentum only has these certain values, that you can derive de Broglie's wavelength versus momentum relationship. All of that comes out of the Schrödinger equation. But the quantumness of it is not because nature is fundamentally discrete or pixelated. It's because when you solve this wave equation in a box or near the nucleus of an atom, you get a discrete set of solutions, okay? That's where the quantumness comes from. So Schrödinger, with his wave equation, is able to reproduce the successes of the Bohr atom with the discrete orbits and things like that. What about the fact that electrons look like particles? So we can do the following thing. That was our analogy. So now let's look at electrons. So we don't need to just think about them sitting in atoms. We can take a little electron gun, cathode ray tube that is shooting out electrons. And we can look at them. This is like a cloud chamber. Cloud chamber is a physics experiment where you sort of supersaturate a gas and then you shoot charged particles through it, and they make little bubbles or little clouds. There's also bubble chambers, which are slightly different, but the same spirit, that leave tracks. And if you put in a magnetic field, then the particles with different charges will be deflected in different directions, etc. And the point is, you can go online, you can look at pictures of particles in cloud chambers or bubble chambers, or modern particle detectors at the Large Hadron Collider at CERN, for example. When you shoot electrons into a detector like this, they leave tracks, which doesn't sound surprising. What else would you expect it to do? Well, tracks are something you would expect a particle to leave, but Schrödinger and de Broglie are saying that electrons are really waves. Is that the actual prediction you would make for a wave? No. The wave would spread out all over the place. You'd see some big puffy cloud. And it turns out, this is just one example, but there's many more examples, when you actually look at electrons, you never see waves. You never see these big puffy clouds. You see particle-like behavior. Schrödinger himself hoped that something like this would happen. The hope that Schrödinger had was that if you started with an electron wave function, so here's space, and you had an electron wave function psi like this, that it would naturally evolve over time into something that was more concentrated. In other words, that the wave function of the electron in empty space would sort of naturally narrow and begin to look more and more point-like, and that would explain why electrons look like points, just because they're waves, but they're waves that are really concentrated near one point. Sadly, this does not happen at all. It's the opposite. If you start with Schrödinger's equation with a little wave packet and just let it go in empty space, it spreads out all over the place. So we're a little bit stuck, and this is why you need to start thinking about interpretations of quantum mechanics. It seems very, very naively that the following thing is going on, that when you're not looking at the electrons, when the electrons are just sitting there in atoms, and you want to explain their energy levels and stuff like that, when you're not looking at them, the electrons are behaving like waves. And when you look at them, they behave like particles. That seems to be what's going on, but that's crazy because clearly whether or not we're looking at something should not be part of the fundamental nature of reality, right? That shouldn't be part of our best theories of physics. So the greatest minds in the history of physics came together and decided that the right way of thinking about this was to say that when we're not looking at the electron, it's a wave, and when we look at it, it's a particle. This is what we teach our students to this day. And some people, like Einstein and Schrödinger, never liked this idea, but nevertheless, this is what we say. So this is the Copenhagen Interpretation of quantum mechanics. And I say that only with some trepidation, because no one really agrees on what the Copenhagen Interpretation is. You know, we attribute it to Niels Bohr and friends, but Heisenberg was just as influential, and in fact, like the first step in this direction probably could be credited to Max Born, who was Heisenberg's collaborator. But the idea is that we need an extra set of rules in physics. So if you do classical physics, Newtonian physics, whether it's fields or particles or whatever, you have two ingredients. You have the system, which is described by a point in phase space, its positions and its velocities. And then you have the dynamical equations, F equals ma, or Hamilton's equations, or whatever. And that's it, you stop. In quantum mechanics, in the Copenhagen Interpretation, you have two different sets of rules. The first set of rules is you have a state, and the state is the wave function, Schrödinger's function, psi of x and t, and you have an equation telling you how that wave function evolves, the Schrödinger equation. It's exactly parallel to classical mechanics. But then, in the Copenhagen Interpretation, in what I'm calling the Copenhagen Interpretation, what you might want to call the textbook or usual conventional interpretation of quantum mechanics, there's a new set of rules, and the new set of rules only has to do with what happens when you observe or measure a system. The rules of quantum mechanics that we teach ourselves have a whole separate category for measurements and the outcomes of measurements, unlike any other theory of physics. And, you know, I'm not saying anything controversial here. This is what you can find in everyone's quantum mechanics textbook. The controversy comes in when you try to say, well, what's really going on when you do these measurements? But for right now, that's not where we are in this video. That's for later contemplations. Right now, I'm just telling you what the rules are, okay? And there are basically three rules. One rule is, let me actually just say, this is for when you measure or observe a quantum mechanical system. Rule one is you see definite outcomes. And I'm trying to translate some very specific mathematical formalism into everyday language here. The point is, you can measure something you call the position of the electron. You can ask the question, where is the electron? You can shoot it through a cloud chamber and look to see where it is. And the first rule of quantum mechanical observations is you see it somewhere. You never see it spread out all over the place, okay? You can think of this wave function, psi of x, as attaching a different value to every possible place the electron could be seen, and the wave function might be completely spread out, but when you see it somewhere. You see some definite outcome for that measurement. Of course, if you never in the real world have perfect measuring precision, right? You never have an infinitely good measuring apparatus, so there's always some uncertainty about the measurement outcome. But that uncertainty is not the famous uncertainty principle, okay? Even in classical physics, your measuring apparatus is never perfect. That's not the point. The point is, if you had a perfect measuring apparatus, you would see a definite place where the electron is. That's the first extra rule. The second extra rule is you cannot predict what that outcome will be with perfect fidelity. All you can do is say the probability of getting a different measurement outcome. So the probability of a measurement outcome is given by a very simple formula. Remember, the wave function, psi, is a complex number, so we want to take its length, we want to square it, and that means square the real part, square the imaginary part, and add them together. The notation we use is we put bars around it. So we take psi And we ask, what is the value of the wave function associated with that measurement outcome? Okay, so you see what I'm doing here. I said that psi was a function of position. That's one way of talking about psi, one way of talking about the wave function. There are other ways of talking about it, which we'll get to in a second. But the point is, if we want to measure the position, we say, well, okay, what is the value of the wave function at every individual position? And the probability of seeing it at that position is the wave function squared. This is the famous Born rule, after Max Born. Max Born is not Niels Bohr. Those are two different people. So it was Born, Max Born, who said that's what Schrödinger's wave function is. Okay? It is a way of calculating the probability of seeing the electron doing different things. It is not sort of something that you have direct access to observationally. And this is the part that Schrödinger had not anticipated and didn't really like. Okay? But this is what we teach our students. And then after observation, afterward, by making this observation, you have changed the wave function dramatically. You get what is called wave function collapse after the new psi equals 1 at that outcome that you saw and 0 for any other outcome. This is called collapse of the wave function. What does that mean? So in pictures, what this means is if before you made a measurement, you had position and you have some wave function like this, psi, and then you measure it, capital Psi. Let's say you measure it and you see that it's here. That's the outcome you actually get in your experiment. Then after you do your experiment, the wave function is not that anymore. Here's what the wave function was. Here's what and here's where you saw it. And here's what the wave function is now. By 1, I mean it is completely localized at that particular measurement outcome. It's not really the number 1 because it's the integral of the wave function has to give you the number 1, not the actual value of the wave function, but you get the point. The wave function goes from being all spread out to collapsing onto the value that you saw. And you can't predict ahead of time exactly what it was. All you can predict is where the wave function is bigger, there's a higher probability of getting that outcome. Where it's smaller, there's a lower probability. So these are the rules, the extra rules dealing with measurement and observation in quantum mechanics, okay? This is why quantum mechanics is weird and hard and controversial, because no other theories of physics have these new sets of rules for the outcome of measurements, okay? It seems that quantum mechanics is trying to say that there is a fundamental divide between what nature really is and what you see when you look at it. It seems, and I keep saying seems because not everyone's going to agree, okay, but the most straightforward way of interpreting this is the electron is a wave when you're not looking at it, but you never see the wave. You see a particle. The things that you see, the set of possible outcomes for measurements, are fundamentally different than the reality behind the scenes when you're not looking at it. Okay, that is the Copenhagen interpretation of quantum mechanics. So this is complicated and controversial for all sorts of reasons. There's a very obvious reason. Let me mention 2 reasons why this might be problematic. I'm not going to answer these questions, but here are the 2 problems. Problem 1 is the measurement problem, by which I mean, come on. What do you mean when you measure something? Like, what is that supposed to tell me? What counts as a measurement? Can I do it with my eyeballs? Do I need a microscope? Do I need a cloud chamber? Can my cats do measurements? Can insects in the room do measurements? Can a video camera do a measurement? What about an atom? Can that do a measurement? What if I only look at it a little bit? Does the wave function still collapse? You haven't told me how quickly measurements happen. What kind of interactions count as measurements? And if you're an undergraduate taking quantum mechanics and you ask these questions, you're told to stop asking those questions. That is not what the Copenhagen interpretation tells you. Now, there are people who want to be more respectable and want to sort of try to answer those questions, but fundamentally, the measurement problem is Number one, measurement plays a crucial role in the rules of quantum mechanics. Number two, we haven't defined what we mean by measurement. That's the measurement problem, and that's an issue. Here's the other problem that I like to highlight that sort of gets swept under the rug sometimes, the reality problem. Now, I spoke in ways, like I said, I hesitated sometimes along the way here because not everyone agrees. I spoke in a way that made it sound like the electron really was a wave when you're not looking at it. That, in other words, the wave function psi, Schrödinger's wave function, really is the electron when you're not looking at it. But you don't see it. You never see psi. You only see different measurement outcomes, like the position. So is it really true that psi is reality, or is Schrödinger's wave function just a tool that we use for calculating the likelihood of certain measurement outcomes? Is psi just a black box? Is it possible there are some other ways of characterizing quantum mechanical states, which, if we knew what they were, would give us definite outcomes for quantum measurements? That's what people like Einstein and also, de Broglie and other people really hoped was going to be true. Other people say, so there's the idea that there's hidden variables in some sense, other variables that are not included in this discussion that would, if only we knew them, give us exactly what the measurement outcome was going to be. That was sort of the Einsteinian, de Brogliean point of view. David Bohm invented a theory like that later on. There's the Copenhagen point of view, which says, don't talk to me about reality. Don't worry about reality. Who cares? Reality, we don't care about that. We care about the observational outcomes. We care about what we see, okay? That's a different philosophy. There's yet a third philosophy that says, actually, let's face the music. Let's imagine that the wave function really is reality, okay? That's the one that I tend to like myself, which is why I tend to talk that way. But I want you to know that there are people who disagree. So, and let me drive home how important that is. Remember, we were talking about these atoms, and we said, there was the Bohr model, okay, or the Rutherford model, the Bohr model, where the electrons were in little orbits, and electrons are really tiny little things. So in this picture that we drew, you can make the statement that atoms are mostly empty space, right? Because there you go, you look at the size of the electron, which is basically zero, the size of the nucleus, which is not quite zero, but still pretty small, and mostly it's empty space in between. The problem with that is, if you believe in quantum mechanics, you shouldn't believe that the electron is a little dot moving in an orbit, okay? You should know better than that. What you should do is imagine, if anything, if we know anything at all, let's see if I can actually do this, yeah. What you should imagine is the electron is sort of in a cloud. Maybe a little bit more likely to be nearby. Okay. But the wave function of the electron is actually the best way to talk about the electron, and that's spread out all over the place. So if you believe that the wave function represents reality, then you don't say that atoms are mostly empty space. Atoms are mostly the wave function of the electron. The electron wave function takes up space in the atom. That's why atoms have a size at all. So even such a simple, straightforward question like, are atoms mostly empty space or not, we don't know the answer to that, or at least we don't agree on what the answer is. Some of us have ideas to what the answer is, but people don't agree, so you shouldn't make very definitive statements about it. Okay, but let me just, that's the basic story of quantum mechanics, but let me kind of emphasize some of the features that come along with this story. I talked about observational outcomes, right? So things like, in quantum mechanics, things like position, I don't need to write things like position, momentum, etc. Don't, some people are gonna give me a hard time for this, but they don't, can you guess what the next word is? Exist. What do I mean by that? I mean, of course you can measure the position of an electron. I already told you could do that. But that's the point. These things like position and momentum, they are observational outcomes. They're possible. Observational outcomes. So in quantum mechanics, there are things you can observe and things you can't. I have not improved my ability to write and talk at the same time. Sorry about that. Things you observe, things you can't. There are outcomes you can possibly get, like the position of an electron. You can ask, what answer do I get when I measure the position of the electron? So we say that position is an observable. It's a thing that can be observed, and you can have outcomes. And the wave function gives you the probability of getting all the different observational outcomes. But if you want to say, well, when I'm not looking at it, okay, when the wave function is some spread out thing, what is the position then? And the best way of thinking about it, and I think this should be true no matter what your favorite interpretation of quantum mechanics is, the best way of thinking about it is there is no such thing as the position or the momentum of the electron when you're not observing it. When you are observing it, you can ask the question, where do I see the position of the electron? Or where do I measure, how much do I measure the momentum to be? But it's not something that has a definite existence when you're not looking at it in the general case. So this is why quantum mechanics is hard, because intuitively, no matter what, no matter how much formalism we've been taught, etc., we tend to treat things that we observe as real, right? That's the world that we're seeing. There it is. And quantum mechanics is drawing this distinction between what we see and what is. Even things that are so tangible and obvious and intuitive, like the positions of things, are only observational outcomes. They are not what really exists. And this kind of way of thinking leads to a very profound and famous consequence called the Heisenberg uncertainty principle, okay? So you can have wave functions that are very close to or even exactly definite in some observational outcome. So you can imagine a wave function psi as a function of x that looks like this, as we drew it before. Something that is very, very close to completely infinitely peaked around some definite outcome. And then you could say, well, it's almost true, or pretty darn close to true, that that particle has a location, the x naught in this particular case. But then you say, okay, well, what is its momentum? And you have no idea what that is. Why is that? So what is really going on? Well, it's because this is a wave function of definite, or pretty close to definite, position. You can also think about wave functions of definite or pretty close to definite momentum, but they don't look anything like this. The wave function is not separately a function of position and momentum, right? Remember I said the wave function is a function of position. You can figure out what the momentum is by telling me what the wave function is as a function of position. So if I have a wave function that looks like a sine wave, this is a wave function of definite momentum. And that is completely compatible with, this is where Louis de Broglie's wavelength comes from, right? Lambda, the de Broglie wavelength, was h over p, the momentum. So there's this inverse relationship between wavelength and momentum. If you have a wave function that has a definite wavelength, that is just oscillating with a fixed wavelength everywhere, then it has a definite momentum. But to have a fixed wavelength everywhere is the opposite of being localized in space. It turns out, this is a little bit deeper than you really need to go, but if you want, so let's think about when you turn on the radio. Okay, you turn on the radio, or not forgetting about the radio. Let's imagine you're listening to music or listening to sounds, okay? You can tell the difference when you listen between a high-pitched sound and a low-pitched sound. Notes of different pitches are things that your ears can discriminate between, right? Even though what is actually hitting your ears is just the density of air at any one moment in time. What's happening is that the density of air is oscillating up and down, okay? You could plot the density of air near your ear and it would be going up and down. And what your ear does is to separate out contributions in the sound waves from different pitches, from different wavelengths, from different frequencies of oscillation. So there is a wonderful mathematical thing called Fourier analysis. Oops, I missed a letter. Sorry, Mr. Fourier. A lot of people named Fourier, actually. So Fourier analysis is a thing that says any function f of x can be written as a combination of functions with definite wavelengths. So this is what your brain and ears are doing all the time. They're taking a function, what is the pressure of air at your ear as a function of time, and they are writing it, they're separating it out into a bunch of different notes, a bunch of different wavelengths corresponding to different pitches of the music or the sound that you're listening to. And this is possible because of Fourier analysis. Fourier transforms, they're sometimes be called, okay? So, in other words, let's say you have some function, f of x, and it looks like, it's small, and then it sort of vibrates a little bit and does something like that. There's x. So you can write that as something with a long wavelength plus something with a slightly shorter wavelength plus something with an even shorter wavelength, etc. I'm not drawing these perfectly, but all these are supposed to be perfect sine waves with absolutely definite wavelengths, okay? And this is called the Fourier transform. And so this is, well, let's just say it. We can take f of x. In fact, let's just be very blatantly on point here. You can take the wave function, psi is a function of x, right? That's the Schrödinger's wave function. And you can Fourier transform it, as we say, to write it as psi as a function of p, the momentum. Because these things of definite wavelengths are, roughly speaking, parts of the wave function with definite momentum. Now, this point that we made up here is that if you are of definite position, or pretty close, you are not of definite wavelength, and therefore not of definite momentum. Likewise, if you're of definite momentum, a smooth curve, a sine wave, then you are not of definite position. So therefore, there are no wave functions with the property that you know ahead of time when you measure the position what you will get, and when you know ahead of time when you measure the momentum what you will get. You can do something that is pretty close. You can have a wave function that is close to being localized in both position and momentum if it sort of looks like this, right? So it's 0 to the left, 0 to the right, wiggles around a little bit. And there is some sort of variation here that is not exactly located in position, but there's a certain uncertainty, if you want to call it that. If you were to measure the position, it would be within that band delta x. And if you did the Fourier transform to write this little oscillating wave packet as a sum of momenta, it would be pretty close to this p here. This is approximately the wavelength, okay, of this particular wave, but it's not exactly. It's really a sum of different things. And so Heisenberg comes along and says that he formalizes mathematically this fact that you cannot both be localized in position and momentum, as delta x times delta p is always greater than or equal to h bar over 2. There's details you have to worry about here. But the reason why I'm doing this is because I just want to emphasize to you that this has nothing to do with measurement all by itself, okay? Heisenberg's uncertainty principle is not the statement that you disturb a quantum system when you measure it. That statement was already made. That statement was in the collapse of the wave function before, okay? Heisenberg's statement is a statement about all the possible wave functions you can imagine. The momentum and the position are not things that exist. They are possible measurement outcomes, okay? And Heisenberg's statement says that no matter what wave function you imagine, it can't be one where you will know ahead of time both the position and the momentum. That's what this is saying. It has nothing to do with disturbing it, but disturbing it is part of what quantum mechanics actually says. Okay. I think we should call it there. I have many more things to say, but that's okay. I've planned ahead of time. This is only going to be one out of. I'm going to try to squeeze the rest of the fundamentals of quantum mechanics into another lecture, into another video, hopefully next week. But this is the basic story, and you can see why things are tricky. Okay, this is why things are tricky right here, because we need to talk about observations and measurements when we do quantum mechanics, and we don't know what that means. That's a problem. And we don't even know what the reality that we're actually describing is. There's a sense in which generations of physicists have been more or less brainwashed into thinking that they shouldn't care about what reality is, that all they should care about are the outcomes of measurements. Okay, Steven Weinberg, the famous physicist and one of my absolute heroes in physics, among all the living physicists right now, he's someone I admire as much as anybody. And he wrote a textbook on general relativity where he makes this attitude very explicit. He's talking about general relativity, not quantum mechanics, but it carries over. He says, all this talk about curved space-time and stuff like that, who cares? I don't care about that stuff. What I care about is making predictions for where spectral lines will appear or, photons will hit photographic plates and things like that. And as much as I admire him, I could not disagree more about that. In my view, physics is about understanding reality. No, 12-year-old girl gets excited about physics because she says, someday I will grow up to make predictions about observational outcomes. What they get interested in is the cool stuff that we learn about the real universe. And quantum mechanics is a place where we haven't yet figured out what the science is trying to teach us about the real universe, what reality what the reality actually is that we are describing with our formalism of quantum mechanics. So we have to do better. We're trying. We're not there yet. Tune in next week. Maybe we'll make some progress.